In the last two lectures, we have looked at how to obtain the equations of motion of multibody systems using the Newton-Euler formulation and the Lagrangian formulation. In this lecture, we will see several examples of equations of motion derived using the Newton-Euler formulation or the Lagrangian formulation. To recap, till now we have looked at the concept of mass and inertia of a rigid body. I have also showed you what is the concept of Newton's law and Euler's equation for a rigid body. We have also obtained the equations of motion, or a way to obtain the equations of motion using Newton-Euler formulation. So in the Newton-Euler formulation, basically we propagate the position, velocity and acceleration in serial chains. We use Newton's law and Euler equations for a free body, and we obtain joint torques. We can also obtain the equation of motion using Lagrangian formulation. In the Lagrangian formulation, basically we obtain the kinetic and potential energy. Then we obtain the equations of motion from the partial and ordinary derivatives of a function called the Lagrangian, a scalar function called the Lagrangian. And then if you have a closed loop system or a system with constraints, then we can use Lagrange multipliers for incorporating the constraints. In this lecture, we'll show examples of equations of motion for a rigid body and rigid multibody systems. The first example is a very classical example. We are going to consider a spinning top. We have already considered seen what a spinning top does, okay, when it is not subjected to an external force earlier on. But now we will look at a spinning top when there is a mg force which is acting at the center of mass here. So if you recollect, the spinning top can be described by z, x, z Euler angles. Okay, so what is z, x, z Euler angles? We can obtain the rotation matrix of B with respect to A. So A is the reference coordinate system and B is a coordinate system attached to the spinning top as some rotation matrix Z about theta 1, okay, about Z by theta 1, rotation matrix X theta 2, rotation matrix X Z theta 3. So where theta 1 is this angle which is also called the precession angle, theta 2 is the tilt or the nutation angle, and theta 3 is the spin, which is the rotation of the top about the Z axis. So if you expand all these things, we have looked at these three simple rotations Z, X and Z, and if we multiply the matrices in that order, we will get a rotation matrix which contains terms like this. Okay, so 3 term is cos theta 2. This is sin theta 1, sin theta 2 minus cos theta 1, sin theta 2. This is sin theta 2, sin theta 3, S2, C3. And 1 term is a little bit more complicated, but we have seen this earlier. It is not completely new. So we have 1 term as C1, C3 minus S1, C2, S3. The 1-2 term is minus C1, S3 minus S1, C2, C3. This term is S1, C3 plus C1, C2, S3. The 2-2 term is minus S1, S3 plus C1, C2, C3. So this is nothing but multiplication obtained from the multiplication of three simple rotation matrices. One's about Z, then about X, and third about again Z. So once you have this spinning top rotation matrix, we can obtain the angular velocity. So we will find A omega B, and this is the body fixed angular velocity, which is nothing but R transpose R dot. Again, we have done this several times, but you can again do it once more, and after simplification, after extracting from this Q symmetric matrix, we will get omega x as S2 S3 theta 1 dot C3 theta 2 dot then S2 C3 theta 1 dot minus S3 theta 2 dot, and then C2 theta 1 dot plus theta 3 S theta 3 dot. Once we have this angular velocity, we can obtain the kinetic energy. To obtain the kinetic energy, we need to know what are the inertia Ixx, Iyy, Izz. So these are denoted by I1, I2 and I3. So in this example, for a top, I1 is normally equal to I2 and which is not equal to I3. I3 is about the Z axis. So once we have this body fixed inertia matrix, we can obtain the kinetic energy, which is half I1 theta 2 dot square plus S2 square theta 1 dot square plus half I3 theta 3 dot plus C2 theta 1 dot whole square. The potential energy for this spinning top is nothing but mgr into C2. C theta 2 is this tilting angle. The Lagrangian can be obtained as Ke minus Pe, and in this case the three generalized coordinates are theta 1, theta 2 and theta 3. Okay, and then we can obtain the equations of motion by doing d by dt of d Lagrangian by dqy dot minus d Lagrangian by dqy equal to 0. So there are no external forces which are acting on this top. So let's compute all these terms in the partial derivatives and ordinary derivatives. So d Lagrangian by d theta 1 and d Lagrangian by d theta 3 is 0. There is no theta, only the Lagrangian is function of theta 2. The Lagrangian with respect to theta 2, partial of Lagrangian with respect to theta 2, you will get all these terms. So you will get I1 into theta 1 dot square into 2 S2 C2 minus I3 theta 1 dot theta 2 dot S2 minus I3 theta 1 dot square S2 C2 plus mg S2R. The partial of the Lagrangian with respect to theta 1 dot is I1 theta 1 dot square S2 square plus I3 C2 theta 3 dot plus I3 theta 1 dot square into C2 square. And the partial with respect to theta 2 dot is just I1 theta 2 dot. Partial with respect to theta 3 dot is I3 C2 theta 1 dot plus I3 theta 3 dot. The time derivative of the partial of Lagrangian with respect to theta 1 dot, again we can compute. Okay, so I am writing this by hand, but you can always do it using some computer algebra tool. So it is I1 into theta 1 double dot S2 square plus 2 I1 theta 1 dot theta 2 dot S2 C2 plus I3 theta 3 double dot C2 minus I3 theta 3 dot C2 theta 2 dot plus I3 C2 square theta 1 double dot minus 2 I3 theta 1 dot theta 2 dot S2 C2. The time derivative of this Lagrangian, partial of the Lagrangian with respect to theta 2 dot is nothing but I1 into theta 2 double dot. And finally, the time derivative of d Lagrangian, partial of Lagrangian with theta 3 dot is I3 into theta 1 double dot plus C2 minus I3 S2 theta 1 dot theta 2 dot plus I3 theta 3 double dot. So we now have all the ingredients to derive the equation of motion. We have the time derivatives. We also have the partial derivatives of the Lagrangian with respect to theta 1 and theta 2 and theta 3. So remember, only theta 2 is there. Partial with respect to theta 1 is 0. Partial with respect to theta 3 is also 0. So the equation of motion now can be assembled just by following the recipe of the Lagrangian formulation. So we can write as theta 1 double dot into I1 into S2 square plus I3 into C2 square, then plus theta 3 double dot into I3 C2 plus 2 I1 minus I3 theta 1 dot theta 2 dot S2 C2 minus I3 S2 theta 2 dot theta 3 dot equal to 0. This is the first equation of motion. The second equation of motion is I2 into theta 2 double dot minus 2 I1 minus I3 theta 1 dot square S2 C2 plus I3 theta 1 dot theta 3 dot S2 plus mg S2R equal to 0. And the last equation is I3 theta 1 double dot into C2 plus I3 theta 3 double dot minus I3 S2 theta 1 dot theta 2 dot. So as you can see, the terms multiplying theta 1 double dot or theta 3 double dot or theta 2 double dot, they are like the inertia term. So that is like I into theta double dot. The terms which are quadratic, theta 1 dot, theta 2 dot, they are like the centripetal and Coriolis term. So we'll have this theta 1 dot, theta 2 dot into some sine theta 2 cos theta 2. Likewise, we also have some theta 2 dot, theta 3 dot in the first equation. In the second equation, we have also theta 1 dot square. Remember, this Coriolis and centripetal term always have quadratic in q dots. Okay, so that is what we see here. And then in the second equation, we also have this gravity term. So this is a term which is coming from the gravity. And the last equation has theta 1 double dot and theta 3 double dot, but also theta 1 dot, theta 2 dot. So apparently this is a very complicated set of three nonlinear ordinary differential equations. Okay, so there are three, and there's a lot of nonlinearity. We have S2 square, we have theta 1 dot, theta 2 dot, S2, C2, and various terms. Okay, so this is one example which has been looked by many researchers in the past, physicists and mechanics people, and lots of people have looked at it, and it turns out this is one of the very few examples which can be solved. You know, in solved, we will discuss what we mean by solved, but we can solve this set of three nonlinear ordinary differential equations. Okay, and let's proceed. Let's see what people have done. People have found out over, you know, maybe more than 100 years back. People have found this out. So first thing that you can see is this partial of this Lagrangian with respect to theta 1 dot. Let's denote that by p theta 1 is given by this. So it is I1 S2 square plus I3 C2 square into theta 1 dot plus I3. Similarly, the partial of this Lagrangian with respect to theta 3 dot is I3 into C2 theta 1 dot plus theta 3 dot. Okay, so it turns out this p theta 1 and p theta 2, so these are basically momentum, okay, corresponding to theta 1 and theta 3. So these two momentum are conserved. Okay, so what do we mean by conserved? This quantity remains constant when the top is spinning. Okay, so this complicated expression of I1 S2 square plus I3 C2 square into theta 1 dot plus theta I3 is remaining constant when the top is spinning, okay, or even tilting or even precessing. So in the complicated motion of the top, this term is conserved. Likewise, I3 into C2 theta 1 dot plus theta 3 dot is also conserved, and it turns out that this is nothing but omega 3. So remember, we computed the A omega B in the body fixed angular velocity vector. The z component of that is this C2 into theta 1 dot plus theta 3 dot. You can go back and see the slide. Okay, so this is also conserved. And finally, like in many other mechanical systems, conservative mechanical systems without any damping, the total energy is also conserved. So kinetic energy plus potential energy is also conserved. So E, which is the sum of the kinetic plus potential energy. So this is kinetic energy. I had shown you the example before. This is the potential energy. So this is also constant. So there are three of these quantities which are constant and they are conserved. So now if you look at this p theta 1 and p theta 3, okay, we can solve for theta 1 dot and theta 3 dot in terms of the conserved quantities. So for example, theta 1 dot is p theta 1 minus p theta 3 into C2 divided by I1 S2 square. So we can write this expression. Likewise, theta 3 dot is given by P theta 3, so which is the momentum corresponding to theta 3, and this is the momentum corresponding to theta 1. So P theta 3 divided by I3 minus P theta 1 minus P theta 3 into C2, and the whole thing into C2 divided by I1 S2 square. So we can write expressions for theta 1 dot and theta 2 dot. And then we can substitute theta 1 dot, theta 2 dot in the expression for the energy. Remember, energy had all these terms of theta 1 dot, theta 2 dot, and theta 3 dot. Okay, so then we can get rid of theta 1 dot and theta 3 dot in the expression for energy and write an expression of energy, which is the sum of the kinetic plus potential energy, only in terms of theta 2 dot and theta 2. So what we will get is half I1 theta 2 dot square plus some P theta 1 minus P theta 3 into C2 whole square divided by 2 I1 S2 square plus P theta 3 square divided by 2 I3 plus mgr C2. So what have we done? So basically E is some conserved quantity, it's a given number. Okay, so this right hand side is a nonlinear ODE for theta 2. Okay, why? Because P theta 1, P theta 3, these are also constants. These are numbers which are constant during the motion of this top. So we have this very, very complicated nonlinear ODE only in terms of theta 2. It is still pretty bad. Why? Because we have C2 square divided by S2 square, and then we have this theta 2 dot square. It is not a simple theta 2 dot. So it's a nonlinear ODE in theta 2 and theta 2 dot square. Okay. But it turns out, and this is what people have found out after a lot of effort, okay, and people have studied spinning tops extensively, that we can make this substitution. Let's call 1 minus u square as S2 square. Okay, S2 is what? Sine theta 2 square. Then u dot will be minus S2 into theta 2 dot, and theta 2 dot square is u dot square into 1 minus u square. Okay, so we substitute what is theta 2 dot and what is S2 square and various other terms, and then we will get this expression, which is u dot square divided by 2. This is given by 2 E I3 minus P theta 3 square divided by 2 I1 I3 minus mgr u divided by I1, and the whole thing multiplied by 1 minus u square, and minus half P theta 1 minus P theta 3 u divided by I1 again whole square. So what do we have here? That u dot square, this term, is basically a cubic function of u. Okay, so how do we get cubic? Because you can see there is a u here and a u square here. Okay, so the maximum power of u on the right hand side is u cube. Okay, so let us denote this right hand side as minus vu. Okay, so what is u dot? Du by dt. So it turns out that we can now solve for dt, not du. So this is du by dt whole square into half. So 2 can go to this side. So we will have 2 into minus some v, which is a function of u. So du by dt whole square. So we will get this expression, which is dt is equal to plus minus du divided by square root of minus 2 vu. Okay, so what have we done? We have obtained du by dt is equal to some expression involving vu, which is a cubic function of u. Okay, so these are called elliptic functions. So those of you who have seen or heard solutions involving elliptic functions, these are very, very complex ways of giving solutions to a differential equation. Okay, so although we cannot really write analytical expressions for elliptic function, but nevertheless we can bring the solution of du by dt in terms of, or we can solve t in terms of u as elliptic functions. Okay. Importantly, we can plot theta 2 for values of e, p theta 1 and p theta 3. So although I said initially that this is a solution of the nonlinear ODEs, but this is not really a solution, because these elliptic functions, we don't know, there are no analytical ways of finding these elliptic functions. So if you have a quadratic, you can say x is minus b plus minus b square minus 4ac by 2. So I can write an expression for solution of a quadratic equation in terms of the coefficients of the quadratic. Elliptic functions are not that simple. Nevertheless, these are known. Okay, there are some things called elliptic functions, and if you can write an expression in terms of elliptic functions, then it is sort of like solution. Okay, and then we can plot. So this is one of the very few examples of nonlinear ODEs or equations of motion which gives nonlinear ordinary differential equations which can be at least written finally in terms of elliptic functions. This example is a modification of a simple pendulum. The modification is as follows. So we have a bob which is connected not by a wire or a rope but with a spring. Okay, so as you can see, there is gravity acting downwards. So the bob can move in some path which is like sort of like an arc of a circle, but it can also go up and down. So there are two variables r and theta which need to be used to describe the motion of this bob. So this r here is the position of the bob along this direction. The free length of the spring is given by L. The mass of the bob is m, and the angle from the vertical of this line, which is sort of the center line of this spring, is theta of t. So the kinetic energy of this bob can be now written in terms of half m r dot square plus r squared theta dot square. Okay, so r dot square is because the bob can go up and down, and also it can have a velocity which is r dot theta dot. Okay, the potential energy of this system is mg r cos theta, and also the energy which is stored in the spring, which is half k r minus L whole square. So note, this is r, the free length is L. So the force which is acting due to the spring is k into r minus L, and of course there is gravity mg, there is mg sine theta and mg cos theta, and r theta dot square which is acting in this direction, and we have 2 r dot theta dot which is acting in this direction. So we have the kinetic energy and we have the potential energy. The Lagrangian then is kinetic minus potential energy. In this case, we are denoting kinetic energy with T and the potential energy with V. The potential energy is function of both R as well as theta. So the Lagrangian is half m r dot square plus r squared theta dot square plus mg r cos theta minus half k r minus L whole square. So once we have this Lagrangian, we can obtain the equations of motion. In this case, there are no external forces. Okay, so we can write d by dt of dou L by dou r dot minus dou L by dou r equal to 0, or we can say this d by dt of this is equal to dou L by dou r. So if you do this, then you will get mr double dot is equal to mr theta dot square plus mg theta cos theta minus k into r minus L. We can also derive the partial derivative with respect to theta dot, partial derivative with respect to theta, and then d by dt of this is equal to this. So then the second differential equation that we will get is mr theta double dot minus 2mr dot theta dot minus mg sine theta. So we have these two equations of motion very easily derived from the Lagrangian formulation, and the Lagrangian formulation inherently you compute the kinetic energy, you compute the potential energy, and then you find T minus V. Okay, so this is a nice and simple extension of a simple pendulum where I can show how to accommodate things like a spring. Okay, let's continue. This is an example of a planar 4-bar mechanism. This is the simplest possible 1 degree of freedom closed loop mechanism. Okay, so there is one loop. So I can start from this fixed end, which is either OL, and then go to the second joint, which is O2, then go to the third, which is O3, and then come back to OR. But this is also fixed. Both of this forms one single loop. So there are three moving bodies, link 1, link 2, and link 3. Theta 1 is the actuated, because this mechanism has only 1 degree of freedom. So we can have only one joint which is actuated. So the other three joints, which is phi 2, phi 3, and phi 1, are passive. Okay, so the geometry and inertial parameters of the rigid bodies are again denoted by mass, inertia, z component of the inertia, because everything is planar, length Li, and II. So I is the z component of the inertia. So it is M2, L2, R2, I2. Likewise M2, L1, R1, I1, and so on. And then there is a gravity acting. And we are going to assume that the CG of each link is located at R1 starting from here. It is located at R2 starting from here, and it is located at R3. Okay, so it is along the link. These are just simplifying assumptions. It doesn't make any difference whether this R2 is somewhere with both an X or a Y coordinate. So we break this 4-bar at O3. So we have a planar 2R and a planar 1R system. Okay, 2R means two links connected by two rotary joints. And this other one is a planar 1R, which is nothing like but similar to a pendulum. So the kinetic energy of this 2R is very similar to what we have derived earlier. All we need to do is replace theta 2 by phi 2. So in the case of the planar 2R, we had theta 1, theta 2. Now we have theta 1 and phi 2. The kinetic energy of the 1R is also nothing but a simple pendulum, so which is half M3 R3 square into phi 1 dot square plus half I3 phi 1 dot square. So what is the total kinetic energy? It is the kinetic energy of these two moving links, which is this 2R chain, and then one moving link, which is the 1R chain. The potential energy is also nothing but the potential energy of this two link chain, which we have derived earlier. Okay, except now we don't have theta 2, we have phi 2, and also this one link chain, which is nothing but mg r sine theta. Okay, r sine phi 1, which is the last output angle. The Lagrangian for the planar 2R plus the planar 1R mechanism is nothing but sum of all these kinetic energies. Okay, so it is half I1 theta 1 dot square plus half I2 theta 1 dot plus phi 2 dot square plus half I3 phi 1 dot square. So this is coming from the 1R chain or from the simple pendulum. These two are coming from the 2R chain. And then we have, of course, M1 R1 theta 1 dot square, M3 R3 phi 1 dot square. This is coming from that 1R chain. And then M1 and M2 are coming from the planar 2R chain. And the gravity terms are coming from the 2R chain, M1 and M2, and M3 is the last chain, 1R chain. For this 4 bar, we have two constraint equations. We have seen this earlier. So basically, the x coordinate of the place where we are going to break is given by L1 cos theta plus L2 cos theta 1 plus phi 2 is equal to L0 plus L3 cos phi 1. And the y component is given by L1 sin theta 1 plus L2 sin theta 1 plus phi 2 is equal to L3 sin phi 1. Okay, so we have the Lagrangian, we have the constraint equations, and then we can perform the partial derivatives with respect to q and q dot. So what is q here? Q is theta 1, phi 2 and phi 1, and q dot is the time derivatives of those. So if you do all these work, lot of work, and again I will show you a way to do it using a computer tool, we will get what a 3 by 3 mass matrix. Okay, so again you can see that the mass matrix has some I2 plus M2 R2 square plus I1 M2 L1 square and so on. So these terms are exactly the same as what we obtained for the planar 2R chain, except instead of theta 2 we have now phi 2. Okay, the 1 2 element is again the same as what we obtained for the planar 2R chain. So 2 1 element is again obtained what we obtained from the planar 2R chain. This is I2 plus M2 R2 square. You can go back to your notes and see that these are exactly the same. This 1, 2, 3 and 4, these 4 elements are exactly the same as what we obtained for the planar 2R chain. This last 0 0 and M3 R3 square plus I3 and this 0 0 is the effect of the last link which we have broken. Okay, so the 3 by 3 Coriolis and centripetal term can also be found out. This will now be again similar to, these terms are very similar to the planar 2R chain, and then this is the other part. Okay, so we have again phi 2 dot, theta 1 dot and so on, and the gravity vector is also here. So we do not have phi 1 dot in the Coriolis centripetal term because that is just a simple rotation and there is no 2 omega cross V rel in that term. Okay. So the equation of motion for the planar 2R and 1R mechanism can be written down. We just collect all the terms which contains theta 1 double dot, which is this, collect all the terms which contains gravity, which is this, collect all the Coriolis and centripetal term which are these, this one and this one, and collect all the terms which contains phi 2 double dot. Okay, so this is from the 2R chain. Likewise for tau 2 we have this gravity term, we have something into theta 1 double dot plus I2 plus M2 R2 square, and then this is the centripetal Coriolis term, and then we have another equation which is simply the single link 1R chain, okay, or this 1R mechanism, which is tau 3 is given by M3G R3 cos phi plus M3 R3 square plus I3 into phi 1 double dot. So these are three nonlinear ordinary differential equations. We have not yet taken the constraints into account, and that is obvious. You can see that the third equation is not yet coupled to these two. Okay, we have broken the joint at O3. Okay, so when you break it at O3, then we have just two individual serial chain systems. We have a 2R mechanism or a 2R serial chain and 1R mechanism. So these equations will be now coupled when we go back and use the constraint equations. So the constraint matrix in this case are the derivatives of the loop closure constraint equations. We will get a 2 by 3 constraint matrix. Okay, so remember it was eta j of q, and then we take the partial of eta j with respect to qi. Okay, so we will get all these terms. So it's a 2 by 3. The first term is this. So this is the eta 1 and then this is the second term and this is the third term. To obtain the derivative of the constraint equations, we take this psi into q dot is equal to 0. So we take the derivative, so we'll get psi into q double dot plus psi dot q dot is equal to 0. Okay, then we obtained q double dot from the equations of motion. Again, very standard. You can go back to the notes and see. So we can write q double dot is some m inverse tau minus cq dot minus g plus m inverse psi transpose lambda. So this is psi, lambdas are the Lagrange multipliers, m is the mass matrix. So we substitute q double dot in this expression here and solve for lambda, and then we substitute lambda back to the equations of motion, and we will get mq double dot is f into psi transpose psi m inverse psi transpose the whole inverse and this. So we have done this earlier. I'm just repeating it once more for this 4-bar mechanism. So in the case of the 4-bar mechanism, psi is 2 by 3. How about mass matrix? It is 3 by 3. There are 3 variables, theta 1, phi 2 and phi 1. Okay, and so on. So what will be this cq dot? It will be a 3 by 1 vector. So again, this f is nothing but tau minus c minus g, and the generalized coordinates for this 4-bar mechanism is theta 1, phi 2 and phi 1. Let's take one more example. This is an interesting example of a thin disk which is rolling on the ground with no slip. This we have discussed earlier. This is an example of non-holonomic constraint. So we have this disk initially in the xz plane. So there is a heading angle which is theta 1, which is rotation about the z-axis. Then there is a tilt, rotation theta 2 about the moved x-axis, and then there is a spin, which is the rotation theta 3 about the moved y-axis. So the generalized coordinates for this problem is x, y, z, which is the center of this disk. Okay, and then theta 1, theta 2, theta 3. So theta 1, which is this one here, theta 2, which is this tilt, and theta 3, which is the rotation of the spin of this disk. So if you have this kind of angles, which is theta 1, theta 2 and theta 3, then the rotation matrix should contain z, x, y. So out of this theta 1, theta 2, theta 3, if you want to actually obtain the rotation matrix, we have to use z, x, y Euler angles. Okay, and this rotation matrix, which is A, B, R. So B is this coordinate system which is attached to the moving disk or the rolling disk, and A is the reference coordinate system. A, B, R can be written in terms of theta 1, theta 2 and theta 3 as sine and cosine of these angles. So we have seen this when we did Euler angles. So C1 is nothing but cos theta 1, C3 is nothing but cos theta 3, S1 is sine theta 1, and so on. So we can obtain the rotation matrix in terms of Z, X, Y rotations about 3 axes, 3 distinct axes using the Euler angle idea, and then we have this rotation matrix. The angular velocity of the disk can be obtained by r dot r transpose. So I'm skipping many steps. We can take the time derivative of each one of these elements. Okay, so C1, C3 will become minus S1 theta 1 dot into C3 plus C1 into minus S3 theta 3 dot. Okay, we have to use chain rule, and we have to find the derivatives of each one of these terms. So this is R11. So R dot means R11 dot. Okay, and then we do R dot R transpose that will be a skew symmetric matrix from which we can extract the x, y, and the z component of the angular velocity vector. The x, y, and z component of the angular velocity vector are given like this. So we'll have c1 into theta 2 dot minus s1 into c2 into theta 3 dot and s1 into theta 2 dot, which is omega y, and c1 c2 theta 3 dot, and omega z is theta 1 dot s2 into theta 3 dot. Again, it's a lot of effort, but then nowadays nobody does this manually. So there are computer tools which we will discuss a little later called Maple, which can be used to perform not only the rotations about z, x, y, and the multiplication of those matrices in that order, but also do r dot r transpose and find the angular velocity components. If you have rolling without slip, then the velocity of this point of contact with respect to the a coordinate system should be 0. Okay, so there is no slip here. So there is no translation velocity between a point on the ground and a coincident point on the disk. Okay, that this is the condition for rolling without slip. So continuing with the example of a thin disk rolling without slipping on a horizontal plane. So we have this disk which is rolling without slipping on this xy plane. The constraint that the velocity at the point of contact is 0, which is the constraint which implies it is rolling without slipping, can be written in terms of x dot, y dot, z dot, which is the coordinates x, y, z are the coordinates of the center of the disk, and we can find out the velocity of this point from x dot, y dot, z dot plus omega times r. We know what is omega from r dot r transpose. Omega is in terms of theta 1, theta 2, theta 3, and also the time derivatives theta 1 dot, theta 2 dot, and theta 3 dot. So if you say that a, b, c is 0, we will get this x dot is equal to r cos theta 1 into theta 3 dot plus r sin theta 1 into theta 2 dot plus r cos theta 1 sin theta 2 into theta 1 dot. Likewise, y dot is rs1 theta 3 dot, rs1 s2 theta 1 dot minus rc1 c2 theta 2 dot, and z dot is minus r s2 theta 2 dot. Okay, again theta 1 is the heading angle, it is the rotation about z axis of this disk. Theta 2 is the tilt, which is the rotation about the moved x axis, and spin or theta 3 is the rotation about the y axis. So there are two constraints. One is the components of the velocity in this xy plane is 0. There is also another inherent constraint, which is that this coin or this disk does not leave this xy plane. So the z is constant, and this holonomic constraint is automatically satisfied when you say the velocity of the point of contact, all three components are 0. The velocity of the center of the disk OB is denoted by x dot, y dot, z dot, as I have mentioned earlier. The inertia matrix of the disk in the body fixed coordinate system can be easily obtained. This is the standard formulas which are available in many textbooks. So the IXX, which is x-axis, and Z, which is this, so XZ plane is the plane of this disk. Both are equal to 1 by 4 mr square, and the IYY, which is perpendicular to this disk, is half mr square. Okay. The kinetic energy of this disk can be obtained by finding what is half I omega square plus half mv c dot square. Okay, so half mv of the center of disk square. Okay, so that is half m into x dot squared plus y dot squared plus z dot square, and then this is half I into omega square, and omega, remember, was r dot r transpose, and we know what is r. It is z x y rotation matrix. So the kinetic energy can be written in terms of m r theta 1 dot theta 2 dot and also x dot y dot z dot, and it is given by half 1 by 8 mr square into theta 2 dot square plus 2 theta 1 dot square plus 2 theta 3 dot square and 4 s2 theta 1 dot theta 3 dot minus c2 square into theta 1 dot square, and then 4 by r square x dot square plus y dot square plus z dot square. So this actually is written such that it is nice compact form which will fit in the slide, but you can see here this 4 and 8 will become half, this r square will go away, so it is half m x dot square plus y dot square plus z dot square, which makes sense. The potential energy is mgr cos theta 2. So again, if you see a little bit, when it is vertical and if it is tilting by theta 2, so then the height above this ground is r cos theta 2, and hence the potential energy is mgr cos theta 2. The Lagrangian can be obtained, which is given by Ke minus Pe. So once the Lagrangian is obtained, we can do the partial derivatives with respect to q and q dot and time derivative with respect to t, and we can obtain the equations of motion. But we also have these non-holonomic constraints, which are basically that there is no slip at the point of contact. So as I said, we obtained that by obtaining the velocity of the point of contact with x dot y dot z dot as the velocity of the origin plus omega cross r, and then we equate that to 0 and we'll get these three expressions. So we can take the derivative of these non-holonomic constraints, and so first we need to write it in psi into q dot is equal to 0, and then we can take psi into q double dot plus psi dot q dot equal to 0. So basically we take the derivatives of these constraints, and then the equations of motion can be written as q double dot as m inverse tau minus c minus g plus psi transpose lambda, and where lambda can be solved as this. So very standard way of deriving the equations of motion of this pure rolling of this thin disk subjected to this non-holonomic constraints of no slip. So I'm not going to write down all the terms because they are very big and they won't fit into the slide, but later on I will show you our computer tools called Maple, which can be used to obtain each one of these terms which go into the equations of motion. So in summary, I've shown you the equations of motion obtained using Lagrangian formulation. We can obtain this error-free equations of motion using symbolic computer algebra systems such as Maple. Equation of motion for a planar 2R chain was derived, for a 4-bar mechanism was derived, and also for the rolling of a thin disk was derived.